So it's for time for the part of the day when we will talk about what we learned and ask for. The microphone ran out of battery, sadly. So you know, Alex was talking too much, and the microphone ran out of battery. I guess I could use this, right? Okay.
Didn't I put it back on after I was done?
Oh well, I couldn't get it working.
Isn't it saying it's full charge?
Well, I don't know. If you can get it working, then so. I'm just an
Check
idiot.
1, 2.
I'm just an idiot, that's all. All right, the failure to identify the on button. Okay, so it's time for the part of the day where we ask you to tell us what you learned. And we'll start with 20 minutes of the geometry exercises from the morning. So I did some number of them standing up here, but there's quite a few that I didn't demonstrate. And oh yes, and I'm going to ask people to volunteer solutions to any of the other exercises that they happened to solve themselves. So yeah, feel free. And can I have any volunteers for any of the exercises? Just tell me if you'd like to volunteer and which exercise you'd like to solve for us. Yes. You finished it, okay, well, then maybe what I'll do is I'll wait till everyone else has had a term and then I'll come back to you for one of the random exercises. Anyone else? Yes.
Sorry, I was trying to find a solution to some of the geometry problems.
Okay. We'll do analysis in a little bit. So let's just do the geometry and then I'll hand over to Alex for the analysis ones. Stephen, okay. That one is a translation, I guess, was the first one. Which one? Isometries? Yeah. Let's see. So isometries are a subgroup of similarities. Okay, great. Let's see. So that was down here. Okay, so great. You proved that isometries are similarities. Okay, great. Tell me how to do it. Oh, sorry, this is translations. Further down, right?
Line 1. Or
yeah, this is it. Okay. Is it this one? Do I have it wrong?
Scroll down. It's in problem 2. Yeah, that one.
Oh, translations are isometries.
No, show that the one you're on right now.
Yeah.
No. The about that. And I can do that one too.
Sorry, which one? That the isometries form a subgroup.
Yeah, that's fine.
Isometries form a subgroup. Okay, great.
Yeah.
Okay, well, pick one and tell me. Okay, so why do isometries form a subgroup?
Well, I guess. Well, we have it for all. I should just talk through the.
Yeah.
Okay. Yeah.
Yeah,
So,
we're gonna try it differently today. So we'll get you to dictate to us what we should type.
So we have a for all. So I guess the first thing to do is intro AB.
I'll call them alpha and beta to keep with our naming convention before. Okay.
Now there are inclusions and inclusions scare me, so we're going to do descent. And maybe even actually descent bracket is isometry. It should catch both of them. Should do everything at once, right? Yeah. Okay. Now we have sort of a couple of implications. So we can do intro HA HB or H alpha H beta maybe. Sorry.
Okay. And so just to display the goal to everyone at this point, now we know that alpha and beta both have this property that absolute value of the difference between the applications is the same as the absolute value of the originals. Okay.
Yeah. And so again, we have the universal converse. So we want to do intro again, and this time I want variables x and y. Intro x, y. So now we can start by so now you want 2 rewrites using the hypothesis. So rewrite and then HA and then H alpha and then H beta should work because H alpha kills off the outer one and H beta kills the inner one.
Great.
So that's the first part.
Okay.
Someone else can take one mem and input if you want, or I can.
Yeah, sounds good. Let's pass on to anyone who wants to do anything else, but maybe ideally one of the other parts of showing that isometries form a subgroup. Any volunteers? Okay, Stephen. Yeah.
I just started out by doing decent. And then I have to show ones on isometry, so I just introduced an x and y. And then I think simp just solved it.
Maybe even dsimp will tell us what one applied to. Yeah, okay. So the one element of the permutation group is the identity. So when you apply dsimp, it just unfolds that to the identity, and we get that x minus y is x minus y. Great. Anyone? Okay, and probably the inv mem is similar. But yeah, any volunteers for any other parts of the geometry file? Anyone? Be bold.
You can say which problem you're interested in.
Oh, well, I want people to volunteer any problems they solved. Yeah. Yeah. Did you solve one of them?
Yeah, okay. I mean, like, I have two, but one is shorter, so maybe I'll give you the shorter. So the one with t less than a.
Okay, so the translations are, which one was A again? A was the similarities.
I think it was kind of the bottom after you introduce this notation a.
Yeah,
Okay,
okay,
so-
great. So you were showing that translations were similarities, is that right?
That's right. Yeah, yeah.
Okay.
So I start with this simp of similarity subgroup.
Okay,
So this
okay. Okay, so dsimp says we need to show that
Oh, yeah.
every translation is a similarity. Okay.
Okay, so we do this simp of similarity subgroup.
It looks like we don't even need to type that because there's no similarity subgroup
Oh.
here. Okay.
So wait. Okay.
Yep.
And then I do intro alpha. Then I do intro beta, intro H.
Okay, so I
Okay.
have to show that if alpha is a translation, then it's a similarity.
Right. So then we rewrite is translation at H.
I'll use dsimp just
okay.
because that's my favorite, but yes.
So then we expand is similarity. So we do rewrite is similarity for this simp.
Okay.
All right.
And now we see
Okay.
what it means to be a translation and what it means to be a similarity. So you've got knowing that every x and y, alpha of x minus alpha of y is x minus y. We're supposed to show this crazy cross ratio property. Okay.
Okay, and then I do intro z w v. Okay, then I do intro h1, h2, h3. And then I rewrite h, z, w. And then I rewrite h, z, v. And that's it.
Great. So what did that do? I guess we've got an alpha of z minus alpha of w here in the goal, and this will turn it into z minus w. And you also have an alpha of z minus alpha of v, and this will turn that into z minus v, and then you're exactly where you want it to be. Very nice. Interestingly, one thing I think I was, yeah, okay, no, that looks good.
So we didn't write down that we used any of H1, H2, or H3.
No?
Yeah,
We can remove it.
I think that I noticed that, I mean, I was translating faithfully from the textbook, but I think one thing I was noticing when I was writing up the exercises is that very, very often it assumes that that the points are distinct, and those hypotheses turn out not to be necessary. So at least in the lean sense. So I think it rather often happened for me that I did not have to use the non-degeneracy hypotheses that the textbook put in, and this was probably one of those cases.
But you can remove false things with that.
No, I think everything is fine. Like I kept in the unnecessary hypotheses because the textbook asked for them, but I don't think they were needed. Okay, other volunteers for other exercises?
I guess I did the one where we choose an element from the isometric group M.
Okay, could we have the microphone over to could we send the microphone? So, and which one was it?
Where we choose an element from M, such that alpha 0 is A, and we want to prove that for all x, alpha x is plus or minus x plus A.
That's this one here, right?
Yes.
Okay, great. Okay, so I forget which one M is. M is the isometries. Okay, so you're saying if you have an isometry which sends 0 to A, then it sends x to either A minus x or A plus x. Okay, great.
Will be seen as H alpha.
Okay, so alpha is an isometry. Great.
And I do this hypothesis where we say H is H alpha x 0, like I evaluate this H alpha at x and 0.
Okay, great. So being an isometry gives you an absolute value condition for any two inputs, and you check it on the inputs of x and 0. Okay. And you wanted me to give this a name, right?
And I call it capital H.
Okay.
And then I do rewrite in close parentheses small h and capital H. Yeah.
Great. Okay, so that changed the alpha of 0 into an A. So now I know that the distance between alpha of x and A is the same as the distance between x and 0. Okay.
And I do this simple operations where I use simp only.
Okay.
Of like h comma sub 0 comma absolute equation of
capital or lower h?
Small h, yeah.
Okay.
Lower h. Comma sub 0. And abs again. Abs equation.
Oh, abs.
Equation.
Eq. Abs. Okay.
At capital H.
Okay. Probably the H is not needed because you already used it, right? But yes. Okay, great. So you were saying, let's use the fact that when you subtract 0, you get the original thing. And I think maybe even more crucially, let's use this characterization of when two absolute values are equal. And so the key point is that that happens either when AX, either when they're equal or when they're equal to each other's negations. Okay.
And then I did dsym.
Okay, so now we're looking at the set in the conclusion. And to be a member of a set with two listed elements, that will turn out to mean that you're equal to either the one or the other. Okay, very good.
This suggests that we have to split it into cases.
Very good, yep.
And I use R cases.
Okay.
H.
Great.
And then I call the first one as P, the first implication. Next, P implies the right-hand side of this statement.
Okay, so you're using the then I'll use this syntax, although I sometimes find it a bit hard, so maybe we'll do some variants. I even am not even sure. Is it like this? Okay, so let's do it this way and then show a few variants. Okay, so in the first case, yep.
This is the right one, and then I use linearity.
Okay, so you're saying if alpha of x, oh, I've done this wrong, right? Because it hasn't named it p. Maybe it's case p, is that?
I use lowercase p, but does it make a difference?
The reason I'm worried is that it hasn't named anything as p, do you see?
Yeah, but after you did something.
Okay, all right. So you selected the right case. Oh, okay, that's funny, okay. So before we had to show either alpha x equals minus x plus a or alpha of x equals x plus a, and you have wisely concluded that in this setting, it's the right one we want to establish. So you chose the right of the two. This is, incidentally, here we're doing an addition to our logic table. We're faced with or, You can use R cases or a couple of variants that I might discuss later. And in the goal, either right or left. So you're handling the or logical tactic, logical symbol. Okay, and then you said you finished off with linearith, is that right? Very nice. And then in the second case,
I call it next Q.
okay.
And the left one.
And you chose the left of the two in this case.
And then I use linearity.
Very nice. Okay, so that's quite right. Maybe I'll just mention a variant of this where this R cases with the next. You can alternatively use, you don't have to, you can sort of do the naming of the cases at the same time as the splitting with a couple of variants, such as, for example, obtain P vertical line Q : equals H. That somehow does all three of these at the same time. This is somehow what I usually do, matter of personal preference, but this is me saying just what you did. H is an OR hypothesis, so let's split into two cases, and in each case give a name to the resulting hypothesis that will come. Any questions about this one here? This is maybe the first one where we have to manipulate absolute values seriously, which becomes a big theme later on in the exercise. Yeah.
Can you use the semicolon thing, kind of the semicolon in brackets to handle both cases?
Say again?
Can you do this like semicolon inside these angle brackets to handle both cases?
A semicolon inside angle brackets.
Like there is this weird notation like angle, semicolon, angle.
Yeah, so the somehow distinction is that the obtain, maybe I'll just add this to my table, obtain, this family of tactics can also be used for and, so maybe I'll, for and hypotheses. But the punctuation is different. So this angle brackets that we were seeing gets used for obtain with existential or and hypotheses, and this alternative punctuation with the vertical line gets used for ors. Okay. Oh, I see. Oh, yeah, sorry, this is a different question. Yeah, so the issue is that that would work if the proof was exactly the same in the two cases. But here the proof is different in the two cases, because in the first case, we end up wanting to choose the right side of the or, and in the first case, we want to choose the left side of the or. So this symbol that you were talking about, like so, would work if after splitting, the proof was nonetheless exactly the same in both cases, which is not the situation here. Maybe one more thing I'll mention is that this cleaning up the subtraction 0, I think that's not strictly needed. So, so it is nice for you to sort of realize that we can clean up the x minus 0 to an x, but Lean is perfectly capable of later on, when it comes time to do our algebra, you know, handling the minus 0 in place. So, you know, I would usually save the 2 milliseconds of my own time and leave the minus 0. And maybe I'll just add, so linearith and linear combination are just further examples of these algebra tactics that we were talking about in the context of ring earlier today. Okay, so this was quite a subtle one, using the or logical symbol for the first time seriously.
More than two cases?
Yep.
What keywords instead of writing?
If you have multiple ors like this, you know, A or B or C or D or E, Lean just treats that as a sequence of nested two ors, and so the tactics are the same. Yep. Yeah, so if you've got an or inside an or inside an or inside an or, you might have this long sequence, you know, right, 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 left or something to navigate to the place where you want it. But yeah. Okay, any other volunteers to show us some geometry exercises? weren't you volunteering in the plaid shirt? Weren't you volunteering?
I can't find the solution now.
Oh, okay. All right. That's too bad. Ella, if you were volunteering to do any of them, right? Do you want to pick one?
Maybe you can. Each isometry is either at right or half tone.
Great. Okay. Okay. So an isometry of the real line either is a move right by A, or else half turn around A. Okay.
I started with by cases because I just decide according to alpha 1.
Mm-hmm.
So I just say by cases, P as a witness of alpha 1 equals 1 plus A.
Okay.
It decide according to different cases. I decide at right.
Sounds good. Okay.
And in the first case, we have left.
So you're saying if alpha of 1 is 1 plus A, then it will turn out to be that we're in this setting, and if alpha of 1 is the other way, then it will turn out. Okay, so we'll say left.
Yes. Maybe we can directly simplify, but I just take x, y because.
Okay, so now we're showing that we have to show that these two functions are the same on every input.
And I simplify these in at right.
Mm-hmm.
And now, again, I decided into two cases whether y is 0 or not. So again, by cases, q is in y equals 0.
Okay.
And in the first case, this is just rewrite of q h and 0f.
I'll use ring, but yep. Yeah. Okay.
And in the second case, I suppose the negation, so the fact is by contra neg.
Okay. And you
I gave a neg.
Okay.
Yes, with q. It's not important.
Oh, sorry. What did you call it? Sorry.
Neg or neg, with q instead of g.
Instead of g.
Q. Not equal. Any q. Any q. Yeah.
Oh, I see. Sorry. Yep. Okay.
Okay. So now, I want to derive a contradiction. To do this, first I have an assumption. Have is 1 equals. I use the previous definition. Is isometry dot eval of eval.
This one here, or this one here?
Yes.
Okay.
I call it at h alpha, h and y.
H and y.
H and yes, y.
Like that. Okay. Okay, so alpha of y is either minus y plus a or y plus a. Okay.
And thanks to my assumption, NEQ, I simplified NEQ at.
Okay, so yes, maybe I'll just simplify this one first so we can see what we're staring at. Okay, so. Okay.
Do you think NEQ?
Okay.
Yes, at this point, I know alpha y.
Okay.
So another have these two in this case, and I called is isometry dot AUX H alpha P and this one.
Okay. Oh, I sorry, I typed it wrong. Okay.
Yes. And now I just simplified these two.
Okay, so you've got that either one is 0, which is clearly wrong, or else y is 0. Okay. Okay.
And now I have the necessary, I can just use q and these two.
Yep, so these two are a contradiction. Okay. Okay. All right.
Should we continue?
Yeah, please. Okay. I'm just trying to think. So I'm trying to think whether it's really necessary to do a case split on whether y is 0 or not. Well, we can talk about that later on. Like maybe it's possible to do this without splitting out the 0 case, but okay.
The other case is just kind of dual.
Okay. So do you want to talk us through it, or? Okay. Well, we can come back to it if we have time, but I know we're at past, so strictly speaking, it's Alex's turn to swap over and to do some analysis exercises.
Okay,
Oh yeah, please. Yeah.
What is simp NEQ doing? What is simp NEQ doing?
Yeah, well, so let's try to break it into several steps. So first of all, if we do dsimp, which we've understood before, so we know that this one says alpha of y is minus y plus a, or alpha y is y plus a. And at the same time, I guess Elif had already proved that alpha of y is not equal to y plus a. So simp is being a little bit clever here, but really what we're doing is, if you know one of two things is true and you also know the first one is not true, then you get the second one. And if I wanted to do this without this powerful tactic simp, I would probably do another obtain h1 or h2. And in the first case, I have a contradiction. And is that right? In the first case, I've shown that, oh, sorry, the second case will be a contradiction. And so all of the not interesting stuff goes into the first case. So that's how I would do this without using the simp tactic. So maybe I'll bring that version back. There. So that's sort of the version without appealing to simp. And now it's called H1. Okay.
One other person, sorry, what's the exclamation point after contract?
Yeah, so this is, so by contra, so we're saying assume for the sake of contradiction. So we want to show this. So we're assuming for the sake of contradiction that it's not true. In fact, I think in this case, the exclamation mark does nothing.
Oh, is that
So,
just part of the keyword or?
There's a slightly more powerful version which you invoke with the exclamation mark. We can talk about it later, but in this case, the distinction does not matter, so I'll just delete it.
Thank you.
Any more questions? And yeah, I will pose as a challenge to the audience to see if you can do it without case splitting on 0, because well, I feel like it should be possible, but I don't want to think about it on the fly now. But very nice work, especially since you finished all of them. Okay. Any more questions about this exercise? Okay, over to Alex.
Yeah, thanks. Okay, you can hear me? All right. And let's get this open. And let's get a fresh Mathlib docs. And let's get a fresh AI assistant, because I can't do them without the AI assistants, as you will soon see. I know that it hurts Antoine every time he sees a chatbot, but I can live with it. What's that?
He's also hurt.
Max. And it hurts Antoine and Max. I will live with it. Okay, let's do it. So are there any exercises that you particularly want to see? There are a couple that they're more than the ones that I knew were wrong. And in really interesting, subtle ways. So it was great to discover those. Should we just go down the list?
I just would like to see some actual uses of filters in science.
Sure. Uses of real filters. Okay. So, right, there's a bunch of stuff that's just proving things are filters. And I guess I did this one already. And it was a little too easy because there's a theorem in Mathlib that says that the inversion at top is 0. So if I put in the name of this theorem, that's not visible in the back, is it? How's that? Where is it? I lost it already. There we are. So there's already a theorem in the library that says the function inversion at infinity goes to 0. In any, you need a field. I guess you need a field because you want to have access to inversion. You need a linear order so you can talk about going to infinity. You need the field to be a topological field, so we have neighborhoods and a strict ordered ring and an ordered topology. Anyway, you need all of these assumptions, but it's a pretty general theorem nonetheless. I don't think the assumption, no, the assumptions certainly don't only apply to the real numbers, for example, but so the theorem exists. But if we didn't want to use the theorem, that's the kind of thing you have in mind, right? So how could we do it? So let's remember what tends to is. Tends to, where's our definition? It's nice to have the definitions here without having to, it's that the pre-image of a neighborhood set we want to show is there. So is there something that tells us how to get the definition of tends to out? I want to say, give me a set. So maybe intro will work. Beautiful. So knowing, let's see, if I unfold tends to, let me delete my proof, or at least let me exit out of here, and I'll just put a sorry. Okay, so we're going to try to prove this without cheating. If you forgot what tends to is, my fear is that unfolding tends to will be a horrible. Yeah, it's not horrible, but it's stating things in terms of maps. And really what tends to, if you remember, like tends to is that the pre-image, so you just think of tending to as being like continuity. The pre-image in a filter is in the previous filter. So that means give me a set and give me that it's in the filter. So that's an intro. Intro U already makes really good progress because now the goal state is something that I can make more progress on. Because it's an implication and you just have a knee-jerk reaction that an implication means that there's a hypothesis on U. So HU or U is in the neighborhood or something, whatever you want to call it. Okay. And then we want to know that U is in this pre-image map. Oh, am I doing the exercise that's not?
Isn't it the same thing that you would have with the unfold tends to?
Well, it has the, yeah, but it has the map. Let's see. I don't like the map terminology because then I have to think about what a map is, but I didn't tell you what a map is. Yeah, if you unfold tends to, then it says the map is less than, and now I have to think about lattice structures on filters, and I don't want to do that. I just want to remember what the definition is. So that's where it's useful to really in your mind have an idea of what tends to is. It's something about a pre-image of a set. So give me a set. Give me a set and tell me that it's in the neighborhood. Now, what does it mean that U is in the neighborhood? Maybe I can simp question mark at U in N. Will it give me that? Nope. How about dsimp? Will that get me anywhere? No. Okay. So I actually have to remember what it means to be in the neighborhood. If U is in the neighborhood, then there's an open set containing U. So what would that be called? Well, tends to has all of these, or neighborhood filter has all of these. If I go to the definition, I'm trying to do it as slowly as possible. It's this intersection filter. Maybe there's something that says neighborhoods, mem neighborhoods if and only if. There's probably a theorem like mem neighborhoods if and only if. So let's see if we can find it in the library. Mem neighborhoods if and only if. It's right there. Mem neighborhoods if and only if. So either I can guess it just from thinking about what it should be called, or I can ask an LLM, but since you're asking this question, I won't ask the LLM, I'll ask this LLM.
So can you actually unfold n to see what it is?
Unfold n?
Yeah.
So you can't unfold n. So if I try to unfold mathcal n at, what was it called, u in n, it's going to say, no, I don't understand.
Can you unfold n0?
Oh, n of 0. No, so n of 0 is not a definition. It's a thing. So, and n is notation. I think you can maybe unfold neighborhoods at u in n. Does that work? Yes. Well, not really, because that doesn't help so much. Right? So I'd rather use a theorem, and the theorem is called mem neighborhoods if and only if. So let's use this theorem. Let's rewrite by this theorem at u in n. And it says, now we know that there exists a subset of u that's open and contains 0. Okay, so we know we have a hypothesis that it exists. How do I get it? Obtain. Okay, so I'm going to obtain the set T, and the fact that T is open, T open, and the fact that 0 is in 0 in T from u in n. All right, so now I have sets u and t. I know that t is open. I know that, oh, and there's even more information. Somehow I didn't break it. Oh, I broke it up in not quite the right way. I got the set t. I called it t is open, but actually it's the fact that t is in u. So let's t sub u will be the name for that. That'll be a little bit nicer. Okay, so we have sets u and t. T is a subset of u. T is open, and 0 is in T. So far, so good. Now I want to know that U is in the member of this at top. Will simplifying that do anything? A little bit. So I just hit simp question mark to find out what lemma's simp is going to call. It's going to call things like one div and filter.mapinv and inv at top 0. I'm afraid this is some powerful stuff that it called that maybe is yeah, at top inverse is well, it's kind of cheating. You're okay with me cheating? Yeah. So now I want to say that U is in the neighborhood of it was completely deterministic. That's right. Sim question mark is not using an LLM. So you're happy using as much, I mean, all the way at the beginning, I think, if I just do apply question mark, I should be able to find a theorem. Let's see. So what I'm looking at when I hit it with apply question mark, let me just kill all of this stuff. Here's how I like to use apply question mark. I look at, this is what the tactic that it says could be applied, and this is what the resulting goals will be. Now that doesn't look that much simpler than what I had before. So forget it. I'm not going to change 1 over x to 1 over e to the x. That's not, thanks for that suggestion, but that's going in the wrong direction. How about this one? I have no idea what this is. E real. Yeah, it's going from reals to extended reals, where you have an infinity. No thanks. Here's another one that's not doing anything useful. This might be useful. For all sets that contain U and are open, there's some large enough n so that for all n greater than n, 1 over n is in U. That seems reasonable. Let's see if I can do even a little bit better. Yeah, please.
Stupid comment, but it took me one. So the crucial point to determine if something is useful or not useful is not really the name. So not the blue stuff, is what comes after.
Exactly. Yeah. I don't care what it's suggesting as the tactic. I'm looking more at what it's saying is the remaining goal. Will that remaining goal be something that looks like I could prove? Okay, does that make sense? Was this this is the, oh, no, the x is going to infinity. So indeed, we are going to neighborhoods of 0. Okay, so this is a candidate. How about this? For all epsilon, there's an n, so that for all n, so on, the distance between 1 over n and 0 is less than epsilon. That looks really good. I don't know that this is an integer, actually. Maybe it is. Let's see. I don't know. N here is a real number. It's just not telling me the type. It knows the type, but I don't. And it's saying for all epsilon, there exists an n, so that for all n greater than that n, the distance, and edist is some extended distance, but I'm sure it simplifies to the usual distance. It's a distance that's allowed to take the value infinity or something. This distance is less than epsilon. I think I could prove that. But let's see what other suggestions it gives. So we were here. Like not monotone, is least upper bound. This is a little bit nicer because now it's a distance. Okay. We can be pretty choosy. How about this one? This is a little nicer. I don't know. It's your question, so you can pick which version.
This one is nice.
This?
This one above.
This one?
Above, yeah.
Okay, great. So we're going to replace the apply question mark by this. What's our first? We have a for all in the goal. So intro epsilon. We have the fact that epsilon is positive. Let's call that eps pos or something. We need to give an n. So what is an n? And we can simp with the subtraction of 0 and the absolute values. We can simp that. So simp a bunch of stuff away. So we want to know that once you're greater than capital N, then your inverse is less than epsilon. What could we use? 1 over epsilon or something. 1 over epsilon plus 1, because 1 over epsilon is not quite enough. Use epsilon. Now, inverse, let's say plus 1.
Should be fine, right? It's all strict inequalities.
Well, that's why I'm worried about, this one is also a strict inequality, so actually epsilon inverse will do. Great. Great. So far, so good? Question?
So how is this suggested search system work? Like, does it search by relative similarity?
Do you mean here when I had the apply question mark? I have no idea. Well, okay, so no, I do have some idea. What apply question? My understanding of apply question mark is it goes through every single theorem in the library. The theorems have hypothesis, 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 and then conclusion. It looks at the conclusion of every single theorem in the library and looks at the goal that I'm trying to work on. And it says, do I have a pattern? Can I match the pattern of the conclusion to the goal that I'm trying to prove? If so, I'm going to show you, what the resulting goal will be.
Automatic ranking of the collaborator. Is there any ranking?
Oh, yeah, maybe Antoine or Filippo or Heather. Does someone know how apply question mark chooses in what order to return?
I think this is a pain point. It really is nearly random at the moment, and there has been talk about, for example, a sensible use case for machine. Yes, I think very, reasonably straightforward machine learning problem would be to make a better than random choice of the ordering of the lemmas, but nobody has done this yet.
But there's also this discrimination tree thing where somehow it like sorts the lemmas based on like the outermost quantifiers. Like if the outermost thing is a plus, then it starts by looking at lemmas that also have an outermost plus.
I think you're right. So you're saying it's slightly better than random at the moment. Okay.
Somehow doing a tree search where it looks for lemmas where like the outermost structure is the same and then the innermost structure it can't quite match.
Yeah. Okay, here we go. Okay, so then we're basically done because now our goal is for all n. So intro little n. And then, okay, this hypothesis on n. And then it's not going to be quite linearith. How about apply question mark? And are any of these good? Let's see. Does this actually did this do anything? No, it just replaced real numbers by extended real numbers with an infinity. Yeah, no thanks. I don't want to do that. I don't want to exponentiate both sides. I don't want to take logs of both sides. I don't want to take hyperbolic sines of both sides. This one is good, I guess. Is that the best one? No, this is what we want, right? Because that's what HN is. HN is this. Now I just need the positivity of N. So what I can do at this point is convert HN. Did we talk about the convert tactic yet?
Isn't that dangerous here? I just think that.
Well, N is positive, so its absolute value is itself.
Okay.
So I'm okay.
Convert. I agree.
In this case, I think I can convert. Convert. Okay, so HN is almost the same statement as the statement I'm trying to prove, but not quite. So convert is going to say, match this pattern to this, and it's going to say, yep, got that, got that. These two things, I don't know why you're telling me that that closes the goal. Are you sure they're the same? So convert on the other side is going to say, why do you think that N is equal to the absolute value of N? And then I need something like abs of pos or something. What's the apply question mark is probably not the right thing. Oh, come on. Go back to the Cauchy sequences that define the real number N. Yeah, rewrite question mark might do a little better. This is where I'm really reaching for the LM because it'll tell me exactly the name and in the right order. And here we go. Abs eq self.
I think you should try
Hyperreal. This is what I was looking for. And now I think positivity tactic should do it.
No.
So no, because of the inverse. Shouldn't it?
I'll explain later. No.
I'm going to try it anyway. Heather says it won't work.
And I wrote it.
Oh, well, okay. Okay, of course Heather's right. Heather's always right. Linearith.
Should do.
N linearith?
No.
No. All right. I need to know that epsilon inverse is non-negative.
Oh,
Which-
because it's not an real. No.
Zero. I don't need to tell it 0 is less than that by sorry. And now linearith will work. And positivity will do this. Beautiful. Okay. So it wasn't at this point in the game. I want to prove that N is non-negative. The reason they can't chain these things together is because that's an inverse. So there's a separate logic to why the inverse is positive. So I added that little bit of information to the to our list of hypotheses, and now you can chain that, and make that. So linearith finishes it. Does that make sense?
There's an order tactic I think, that you can do. So I've actually never used this tactic before, so this is for me to experiment as well. Can you try changing linearith to order?
At this point?
The last
the
linearith.
last thing?
Yeah, so this order to, because
Okay.
we're using something much weaker than the full power of like the revised simplex method. We're really just using sort of chaining inequalities by transitivity. So this order tactic, I mean, I think is all we need. It's much weaker, should be faster than linearith, and yeah, it's the first time I've tried it, but it seems to work.
What about something like hammer? Well, I have to install hammer. Okay, so I don't have hammer going here. Or not ASOP? Is it, like, what's the most automation that I could do instead of doing, like at this point, I would like to think that something completely automated would do it. I'm going to upset some of you by copying the goal state and going here and saying, help me prove this theorem in Mathlib 4.
Somebody should add an LLM tactic.
Well, I think it actually already exists probably. Blah, blah, blah. So let's see. This is what it suggested. Let's see if it's right. So we're
This is not automation. I mean, this is.
Yeah, it's down. I mean, it's not using any tactic.
So it unknown. No. But this is exactly what I didn't say it gets it right. I said it makes it useful. So now I say error, unknown identified. It says, oops, I made up a name.
About the name.
Yeah.
It really says the inverse is less if one leaves the inverse is less. If you look at inVLT of inVLT,
Yeah.
means well the inverse
Is it still using the same name?
Yeah.
InVLT?
No, it defined.
it defines something, but if you
yeah.
think of what this lemma would mean in Mathlib.
Yeah. Exactly right. Exactly right. It guesses the name of a theorem that probably should be in Mathlib.
No, it's there. It's just it's got a subscript zero. Go back to your proof, and you'll see there's the same thing with a zero on it.
Oh, that zero was from the refine. So I think it has an old version of Mathlib that it's been trained on, and since then they changed it and put a zero there, and that exactly solves the goal. So that the LLM actually did it. Okay, it just did it on a version of Mathlib from 6 months ago that didn't have it.
But it made a worse proof. Is what I'm saying. The proof we had ourselves.
By the time I'm here, I don't care what the proof is. I wouldn't continue with the calculation as a human. I'd say, and this is obvious. So I'm sorry, it did do it. Okay.
Alex?
Yes, please.
I mean, as we were talking about the other day, if you did that in quad code, it would have done that step where it randomly saw the error and then was like, oh yeah, duh. And then
That's right. That's right. So I don't use Claude Code because I like to be able to go back and forth and just look at what it's doing and grab the pieces of it that's useful to me and ignore everything else that it says, because most of the time what it says isn't quite right. But I know how to correct what it's saying and put it in the place where I want it to be. In this case, it one-shot it modulo the fact that it didn't have the sub-zero, the subscript zero. Okay. Sorry for those that had to bear witness to an LLM working on mathematics. Okay, should we do another? We have 5 minutes. Yeah, please.
Why do they have a sub-zero?
Why was the sub-zero added? Anybody want to field that one?
Oh,
Yeah. Sorry.
You should explain that.
So is this because of group with zero?
Yes.
Yeah.
Okay. So this is actually really interesting, and maybe somebody should give a lecture about this, who's not me, that Mathlib realized that there's a mathematical structure, a fundamental mathematical structure, as fundamental as group, ring. No, because it's everywhere. But it is everywhere. This group with zero is something that's used all over the place. Yes?
I think that was the function name in Mathlib 3. So maybe Claude cannot tell like what's Mathlib.
Well, you notice I did say Mathlib 4.
You said it like.
I gave it the number 4 so that it would know not to give me old lean code. That doesn't mean it won't.
But I'm sure.
But-
That is true. If you search Mathlib 3, there is really a function for that.
And I think Mathlib 4 also had a function with exactly that name until rather recently. So there's a recent change. Yeah.
Putting a zero to statement that
Yeah.
apply to group with zero. Or zero.
So someone else can maybe at some point, I mean, not now, we can have a conversation about what these other structures that exist all over the place in Mathlib that are not structures in the rest of mathematics, like a group with zero.
Post moon reflect LT.
Exactly.
For instance.
Yeah. Yeah. Okay, let's do another one. We have 2 minutes. Should we do another one? Let's finish on a purely LLM. You want to see what it can do? All right.
What if you have 2 minutes? I mean, I don't know when you.
Okay, let's just throw this at it. It doesn't know what seq-lim is. So actually, it should guess. It should guess what seq-lim is, even though it doesn't know. I mean, you want to play this game? It will win.
10 liters of water.
If it does it?
No, just asking is 10 liters of water and the energy consumption.
Oh, I heard.
capacity.
Oh, no. I heard 10 liters of vodka. I thought you were betting me. And I was going to take that bet because that's a lot of vodka. help me prove this theorem. I don't have to spell theorem correctly. It'll figure it out. Yeah, it says, I don't know how you defined it, but
Well, the first is
if it's an epsilon n definition, then I'm going to guess that it's this. You don't, well, okay, let's see. So I have to tab things over and it one-shot it. It did not know the definition. It just guessed what you might normally put there as the definition. And in one shot with 6 lines of code, 6 lines of code, said, okay, I think what you want to do, even though I don't know your definition, I'm going to apply this metric.tends to at top, and that's going to turn tends to into for all there exists. Now, actually, I think at this point, I could practically say convert H would be maybe a faster proof, convert H and it's done. Yeah, so I don't have to, there's nothing to convert, it's actually exact. I thought it would complain because this is in terms of a distance, but of course the distance on the real numbers is the absolute value, which is what we've put into the definition. So exact H will do it. Okay, there's a faster proof than the one the LLM came up with, but because it didn't know exactly what our definition is, it guessed, give me an epsilon, give me the n, use that n, give me the n and the hypothesis on n, and then use it.
So Alex, does that mean that the whole proof can be rewrite by that lemma and then REPL?
Yeah, is it a roi?
No, before the constructor.
Oh, before the constructor. Rewrite by this lemma, probably. Rewrite by this lemma, and then REPL. Yep. Okay, so the point is, the library is strong enough that these things are there. That's the beauty of Mathlib. The reason we are not now at the point where LLMs are getting better, but also Mathlib's getting better, and they're both getting better, and it's just becoming really easy to do math in these systems. If you don't want to contribute to Mathlib, you don't want to know what's in there, you don't want to obviously work on, maybe not obviously, some of you may want to work on LLMs, good for you. But these things together now turn an idiot like me into someone who can do formalization rapidly and without, constantly being stuck. And with that, it's 5 o'clock, so maybe we should get a drink. Oh, yeah.